actually maybe on a day I wouldn't have class. Like, smart.
We should take the class picture today.
That's a great plan.
Yeah, I was gonna warn people that I do take the class picture, but yeah, as Devin knows and Dan, we took the class picture in the last class. Got to. Okay, well, let's get started, right? That clock is already past time. We're 1 minute past.
Is there an event this morning or something?
The skip linear algebra event?
No, I mean...
Yeah, I have no idea. It may be that people, are feeling the crunch and rely on the video, right? They know that there's going to be a video, so. You guys, come to class.
Is our participation grade determined on us being in class? Or is, like, actually
yes, actually,
participating?
yeah, and participating ideally. If you come to class and just sit in class, well, that's a kind of participation. But even better is if you are actually like engaging and talking and trying to throw out wrong answers. Right? If you throw out a lot of wrong answers, that's actually pretty good. Okay. Okay, well, there's only 5 of you today, but let's get started. 6. Okay, so let's recall what we finished up with. So remember what we finished up with was this corollary. And the corollary said that if A is Hermitian, if A is Hermitian and has all distinct eigenvalues, then something happens. Right? Does anybody remember what happens? Does anybody remember what happens? If A is Hermitian and has n distinct eigenvalues, then something happens. Maybe remember? There's few of you today, so maybe the chances are even lower than usual. Maybe remember? So we had a theorem right before that said that if A is Hermitian, then eigenspaces are orthogonal, right? That eigenvectors corresponding to distinct eigenvalues are orthogonal. Julie?
So you can get an orthonormal base.
Exactly. Then you can get an orthonormal basis, right? So then you can get an orthonormal basis, right? And you can use that to make a matrix, right? You can make a matrix. You can make a matrix, of orthonormal columns, okay? And that thing will diagonalize your matrix, right? That will diagonalize your matrix. So there exists, an orthogonal matrix. That diagonalizing A. Okay. Now I put this term orthogonal matrix in quotes because it's actually an orthonormal. The columns are orthonormal with respect to the complex inner product. Okay, so that's a little bit different from what we had earlier. It was our orthogonal matrix was where the columns were orthogonal, were orthonormal with respect to the real inner product. So this is actually something slightly different and has a name. So let me give the name. If you have a complex matrix, okay, and columns are an orthonormal basis in Cn with respect to the complex inner product, then we call U unitary. Okay. We call U unitary. Okay, so really we shouldn't use this term orthogonal matrix, we should say a unitary matrix. A unitary matrix. Okay. Unitary matrix. Okay. Okay. So is that clear? Everybody gets that? Right. This is what we finished up with at the end of class last time. Okay. And the only thing we've just done is introduce this term unitary. It basically means an orthonormal base. The columns are orthonormal with respect to the complex inner product. The complex inner product. Okay. Okay. So just notice that unitary means that U conjugate transpose U is the identity. Right? That's exactly what this means, right? Okay. In other words, that U is the identity. Okay. In other words, that UH is U inverse. Okay, the conjugate transpose. If your conjugate transpose is your inverse, then you call it unitary. Okay. Okay. So I'm going to erase the stuff on the left unless anybody protests. Because I want to start basically a new board to get to the next theorem, start the next theorem. Okay, so what we just said is that if you have a Hermitian matrix and it has, so you have a Hermitian n by n matrix and it has n distinct eigenvalues, then it's diagonalizable by a unitary matrix. Okay, it's diagonalizable by a unitary matrix. This is called unitarily diagonalizable. Okay, as a long term. It's not just diagonalizable, it's unitarily diagonalizable, okay, which is a little bit better. Okay, but in fact, there's something even more amazing. Okay, and this is called the spectral theorem. The spectral theorem. If A is Hermitian, then it is unitarily diagonalizable. Okay. In other words, any Hermitian matrix is unitarily diagonalizable. Okay. Doesn't have to have n distinct eigenvalues. As long as it's Hermitian, right? As long as it's equal to its conjugate transpose, then it's unitarily diagonalizable. Okay. Okay. So that should be kind of a shock to you, right? That should be sort of shocking. Like, what? How is that possible, right? It's not. We don't need our n distinct eigenvalues. It's anybody. Any Hermitian matrix is unitarily diagonalizable. Okay, so this is one of the classic big results of diagonalization. Okay, so okay, let me write it in a more dramatic manner. Every Hermitian matrix is unitarily diagonalizable. It's the same thing, but just more dramatic. Okay, so what we are going to need is the following lemma. Okay, and this lemma is so strong that it's actually called Schur's theorem. We're going to use this thing to get the spectral theorem, and here it is. It says this: that given any n by n matrix, there exists a unitary matrix U such that UHAU is upper triangular. Given any matrix A, there's a unitary matrix such that UHAU is upper triangular. Okay, maybe if you wanted to say this in English, you would say all matrices are unitarily triangularizable. Right? All matrices are unitarily triangularizable. Okay, I don't think people say that, but that would make sense. Okay, you can always get a unitary matrix that when you conjugate A by it, turns into an upper triangular matrix. Okay, so the proof of this is, we'll do this by induction. Okay, we'll do this by induction on n. Okay, if n equals 1, then we are done already, right? Because your matrix is already upper triangular. It's a 1 by 1 matrix, it's automatically upper triangular. So there's nothing that needs to be done. Okay, so case n equals 1, done already. Right? You don't need to, right? You could say you could use the identity matrix on both sides. Okay, so so assume a statement for assume a statement is true for k by k matrices. Assume the statement is true for k by k matrices, and let's let A be a k plus 1 by k plus 1 matrix. Okay, the proof of this is kind of funny, so let's show you how you do it. So let's let lambda 1 be an eigenvalue of A, and suppose that W1, the vector W1, is in E sub lambda 1. Okay, right? You're going to have eigenvalues. You know, choose one of the eigenvalues. Choose an eigenvector corresponding to that eigenvalue. Okay. Now, by Graham-Schmidt process, using the Graham-Schmidt process, we can create an orthonormal basis, starting with with W1. Okay, I guess assume that this guy is norm 1. Okay, right, because we want to make an orthonormal basis. Well, just normalize this guy. Make sure that it's norm 1 to start off with. Okay. So you guys remember, I hope, the Gram-Schmidt process, right? You have a basis, and then you can change it into an orthonormal basis. Right? You can make an orthonormal basis out of it. Okay. So we can make an orthonormal basis. Let's call this orthonormal basis W1, W2 to WK plus 1. Then let W be the matrix with Wi as the ith column, right? For I equals 1 to k plus 1. Then W is unitary. Okay, anybody confused? Anybody confused? Right, we took an eigenvector, we made sure it was norm 1, we built it up into an orthonormal basis, right? We made an orthonormal basis starting off with that eigenvector. Then we use those guys as the columns. Well, we've got a matrix with an orthonormal basis as its columns. That's, by definition, a unitary matrix. Okay, so nothing amazing has happened. Okay, so now we're going to use that guy, and remember the first column is an eigenvector. So now we consider WHA, whoops, that's not an A, WHAW, right? Right. We conjugate A by this unitary matrix. What's the first column? What is its first column? You should be able to tell me what the first column looks like. Okay. We're basically taking the matrix representation of A with respect to this orthonormal basis. What's it going to look like? The first column of W, remember, is W1, which is an eigenvector, right? Which is an eigenvector. Talk to each other for 30 seconds. Okay, anybody want to say? Julia, you look no, you're not. Okay. I was going to say you look kind of cheerful, but no. You're maybe cheerful, but not sure. Remember, what's good about having an eigenvector basis? When you take the matrix representation with respect to it, your matrix representation is diagonal, right? Yeah, right? It would be diagonal. That's why we have, wait, did you say
that? Is the eigenvalue.
It's diagonal. That's right, Nico. Okay, right? It's diagonal, right? Okay, well, we don't have an eigenvector basis, but the first guy is an eigenvector, right? And so what's it going to look like? Well, you're going to have the eigenvalue. This is maybe what you wanted to say, right? Right, you're going to have the eigenvalue, right, here, right? That's what happens when you have an eigenvector basis. Well, we just have part of an eigenvector basis, so we'll have part of a diagonal. We'll have a part of a diagonal matrix. Okay. Okay. And then for the rest of it, we don't know, right? There's some other stuff. Okay, we don't know. So I'm just going to write it like this. We're going to have stuff in the first row, and down here we're going to have some matrix that we don't know also, called M. So by your knowledge of matrix representations, this thing is going to look like this. So since W1 is an eigenvector with eigenvalue lambda 1, when you diagonalize, when you conjugate it, you're going to get this thing. Okay. And maybe you see what I'm going to do. This guy, M, is a k by k matrix. Right? M is a k by k matrix. And so what? So we're going to use the inductive hypothesis, right? Right? We know that we can upper triangularize M. We can unitarily upper triangularize M because it's a k by k matrix. Okay. So by the inductive hypothesis, right? We know the statement for k by k matrices, so there exists a V1, a unitary V1, that's a k by k matrix, such that V1 HM V1 is upper triangular. Okay. 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 Now, let V be the k by k matrix. I'm sorry, the k plus 1 by k plus 1 matrix that looks like this: 1 0 0 0 0 0 V1. Okay. What are we going to do next? Anybody see what we're going to do? If we conjugate A by W, we get this thing. If we conjugate M by V1, it's upper triangular, right? So let's take this thing and conjugate it by this guy, right? So what we're going to do is we'll take WHAW and conjugate it by a V, right? This thing will equal right, VH times that guy V, right? But when you do that, you end up with lambda 1 0 0 0 0 B1 H B1. Actually, I'm not sure about these zeros, so let me just leave them out. It doesn't matter. You get some stuff up here. Okay, so, and this thing, this guy is upper triangle, right? Where V1HM V1 is upper triangular, right? So let me say it this way. Which is upper triangular, which is upper triangular since V1H and V1 is. Yeah, Dan.
Sorry, I have a question. So why does the eigenvalue not have any potential for a for some sort of coefficient on that? Is it just because we arbitrarily set the 1 spot of V to V1?
Yeah, exactly.
Okay, so it could have a coefficient if V wasn't that way.
Yes, yes.
Okay.
Yeah, we did that intentionally, so that we wouldn't affect this thing. We could. I mean, you could put a number on it, but why? Right? I mean, it would still be upper triangular, but why would you want to do that? It doesn't matter. Yeah, yeah. No, it's good. It's good. Okay, everybody okay? Right? So, okay. So what we've done is we've conjugated A by WV and gotten an upper triangular matrix. Okay, so the only thing we need to do is check. We need only check that WV is unitary. Right? Remember what our goal is. Our goal is to show that any matrix is unitarily triangularizable. Right? Okay? And what we've done is we found a matrix that we can conjugate A by and get it to be upper triangular. So as long as this guy is unitary, then we've shown that that A is unitarily triangularizable. Okay. Any questions? I feel like people. I'm not sure if people are following. Any questions? Okay. So let's check that this thing is unitary, right? So. Well, if we look at VWH times WV, H times WV, what do you get? What's the conjugate transpose of WV? Can anybody just tell me immediately? Yeah, Julia.
Is it V bar transpose?
I'm just going to call it H. Yep.
Okay, and then W.
Exactly, WH. Right? Because all this is conjugate transpose. And you know that the transpose of a product is the product of the transposes in the reverse order. So the conjugate transpose behaves like a transpose with regard to, products. Okay. Okay. So you get this, right? Right. But you know that this is unitary. Right? This is unitary. Oh, now I see what. You know that this is unitary. So this is just the identity matrix. And so you get VHV. V is also unitary, so you get the identity matrix. Okay. So, right. So WVH is WV inverse, right? So WV is unitary. Okay, and that's the end of the proof that every matrix is unitarily triangularizable. Okay. Yes.
I just said that'll be a fun one to write on the test. It's so long.
Oh, you mean just the words or the
Just
actual?
the whole proof.
The whole proof. Yeah, that's not going to happen. Yeah. Getting back to Dan's comment, so I said something that was completely wrong, that I said you could change this number and it'd still be okay. It wouldn't be okay, because then the V wouldn't be unitary anymore. We need it to be unitary, right? So we need every column to be norm 1, right? This guy is perpendicular to the other guys, that's clear. We also need it to be norm 1. Okay, so that is that's Schur's theorem, right? Schur's theorem. Any complex matrix, for any complex matrix, there exists a unitary U such that UH a U is triangularizable. I'm just writing it again. You have it. You have it already. Okay. Remark. What this also says is that any A can be factored into A equals U A U H. Oops, U T U H, where the U is unitary and T is triangular. Right, that any matrix has a factorization like this. Okay, any matrix has this sort of factorization. This factorization is called the Schur decomposition. Of A. Okay, so now let's get to now we're going to use Schur's theorem to prove the spectral theorem. Okay, so recall the spectral theorem. Every Hermitian matrix is unitarily diagonalizable. Okay, we've just seen that every matrix is unitarily triangularizable, upper triangularizable. Okay. Now we're saying that every Hermitian matrix is unitarily diagonalizable. Okay. So the spectral theorem is actually an immediate consequence of Schur's theorem. It'll take us like 1 minute to write up. 1 minute to do. So say, okay, say A is Hermitian. Suppose that A is Hermitian. by Schur's theorem, there exists a unitary U such that UHAU is upper triangular. Okay. But notice, so TH, what's TH? TH, well, that would be UHAUH, right? Well, what's that?
H-U-H.
Exactly, right? It'll be U, H, H, but two H's will cancel each other off, right? Conjugate transpose of a conjugate transpose is just your original matrix. So you get U, A, H, U, H, right?
Do you have to swap it?
In the opposite order, thank you. U, H, A, U. Oops. U, H, A, H, U. Right? But what's A, H? A. Right? So you get U, H, A, U. But what's that? T. Exactly. T. Okay, so what you notice is that T is Hermitian. T is itself Hermitian. Right? But if you have an upper triangular Hermitian matrix, an upper triangular Hermitian matrix, right? Remember what Hermitian means. It means that its conjugate transpose equals itself, right? So you flip it across the diagonal and take its conjugate and it equals itself. And it's upper triangular, right? You have an upper triangular matrix. Everything down here is 0, right? And you flip it over, take the conjugate, it equals itself. What do you see about it? It has to be diagonal, right? All these guys above the diagonal must be 0, right? So it has to be diagonal, and of course yeah. So, and thus T is a real diagonal matrix, right? So Schur's upper triangularization actually resulted in unitary triangularization actually resulted in a unitary diagonalization. That T that we got was actually diagonal. Okay. So if your matrix is Hermitian, then the triangularization actually results in a diagonalization. Okay. So that is the great spectral theorem. Any questions? Any questions? Let me go on. Remark: there is an analogous theorem for real symmetric matrices. So there's another spectral theorem that any symmetric matrix, any real symmetric matrix is orthogonally diagonalizable. Right? In other words, i.e., there exists an orthogonal Q such that Q transpose AQ is diagonal. Okay, but we're not going to prove it. We're going to skip the proof of that. Okay, so there's the spectral theorem for Hermitian matrices. There's the spectral theorem for symmetric matrices. But we're going to skip it. Okay, let's go on. Okay, so what we just saw that if you are Hermitian, then you are unitarily diagonalizable. Okay, but it's not true that. So what we have here, right, is Hermitian implies unitarily diagonalizable, unitarily diagonalizable. But the reverse direction is not true. It's not true that if you're unitarily diagonalizable, then you're Hermitian. Okay. There is something else, and that's something called a normal matrix. So normal matrices. Okay. So here's the definition. If A times AH, its conjugate transpose, equals AH times A, we say that A is normal. A is a normal matrix. Okay, and we'll have a kind of cool theorem that says this, that A being normal is equivalent to A is unitarily diagonalizable. In other words, there exists an orthonormal basis of eigenvectors. Okay, so right, we'll be able to understand exactly what it means to be unitarily diagonalizable. Okay. Let me ask you a dumb question first. If A is Hermitian, is it normal? Sure. Right? If A is Hermitian, is it normal? Well, if A is Hermitian, then AH equals A. Right? If A is Hermitian, AH equals A. And we're asking, does AA equal AA? Right? Then the condition of normalness would be, does A times A equals A times A? And of course that's true. Right? So yeah. Okay. let me also say that what this is saying is that you see what it means, that you can change the order, right? That you commute with your conjugate transpose, right? If you want the language for this, A commutes with its conjugate transpose. A commutes with its conjugate transpose. Okay, so I don't think we'll have time to do both directions. Maybe we will, I don't know. Yeah, Julie?
So this also means that just because it's normal doesn't mean it's Hermitian, right?
Yeah.
Okay.
Yeah. So Hermitian implies normal, but normal doesn't imply Hermitian. Right? Hermitian is actually strong. So being Hermitian is stronger than being normal. Right? If you're Hermitian, you're normal. Right? But not the opposite. Okay. Okay. So let's see how far we can get here. Suppose you have an orthonormal basis of eigenvectors of A. Okay. Use them to create a unitary matrix. U. Right? So use those guys as the columns, to create a unitary matrix. Okay. Then, what do you know? You know that UHAU is diagonal. Right? We have 2 minutes. I'll give you 1 minute to tell me that A is normal. Show that A is normal. Okay, take a minute and see if you can finish it off. Actually, let me do it because I also want to hand back some homework. Sorry. So let's see that A is normal. Okay. Well, what's A? A is UDUH, right? A is UDUH, and we want to show that, right? We need to show that AAH equals AHA. Right? That A equals AHA. Okay, so let's write that out. AAH does that equal AH A? Okay. Well, what we get is UDUH, UDH, UH. Does that equal UDH, UH, UDUH? Okay. Just using the conjugate transpose on a product, right, as we had before. but UHU is what? U is unitary, so UHU is the identity matrix, right? UHU is the identity matrix. And so what we get is, our question is, does UDDH equal UDH right? Right? So our question boils down to, does DDH equal DHD? Right? If you take a diagonal matrix, right? If you take a diagonal matrix and then multiply it by its conjugate transpose, is that the same thing as, the product in the opposite order? And that's true, right? That's definitely true, right? So the answer is yes, right? Okay, so A is normal. Okay, and next time we'll say the opposite, that if you're normal, then you're unitarily diagonalizable. Okay, sorry to keep you over. If you can stay a little bit longer, I've got a stack of homeworks to hand back. If not, I'll give it to you next time. There's a bunch of them, so okay, maybe more than one. Avery. And that's it.